The 5 pictures in this slide are of the people most important in the development of the expansion of the universe theory. First, of course, on the upper left corner is Albert Einstein, a graduate of Polytechnic in Zurich, no PhD, worked as a patent clerk, got a job as a visiting professor later on, and only after his great discoveries did he get an actual position as a professor of physics. He invented the theory of gravity that includes relativity and E equals mc squared, from which the expansion of the universe came. Second, to his right, is Friedman. He was a young mathematician in Russia just before and after World War I, and he developed the first mathematical expansion of the universe theorem using Einstein's equations. Einstein himself created a model for the universe, but his model was wrong. Next, to the right of Friedman is Lemaitre, who was actually a monk or a clergyman in Belgium. He got his degree in physics, became a clergyman, and then came back to study in Cambridge, and was the one that made the connection that not only is the universe expanding, but it should have been very small, incredibly dense, and hence he had the original nucleus. Next after that is Robertson. Robertson was from Washington State, and he came up with the correct mathematics that would combine Einstein's and Friedman's ideas. Later on, after he published his famous papers, he became a worker for the State Department and then the CIA, basically figuring out the effects of weapons systems. It started just before World War I, but he continued all the way until he passed away in the 60s. Last one, Walker, an Englishman, he was the one that put all of the proper math together so that the model works. Yes, it ends up still being Adam, Eve, and a snake. But guess what? If we did the full math here, it would take at least another 4 semesters. Now I take that diagram that I've shown you of the expansion of the universe causing the faraway galaxies to move faster, and go not to 1/10 the size of the universe, but further out still. There is a situation here that we have to take into account. Is the universe expanding at a constant rate exactly? You have to take a couple of things into account. First is that the speed of light is finite, so we see the very far away galaxies as they were billions of years ago. And the other thing is that if the universe, for example, is accelerating its expansion or slowing down its expansion, at the very end of the Hubble diagram there'll be very different kinks to the graph. That's what is on the right side. Now, of course, if the universe is going to slow down its expansion, the right-hand side diagram is a very intuitive picture of that. The blue circle represents a universe that expands and then collapses on itself. And then the pink one is a universe that would basically remain exactly in the borderline. And the next one over is a universe that is basically never going to collapse back on itself. We are not even in the last one. Ours is not even in there. Our universe is actually speeding up its expansion at the moment. This diagram actually gave Adam Rees and Saul Perlmutter the Nobel Prize in Physics for 2012, I believe. Basically, this is a diagram that's very similar to the Hubble diagram. It's, if you may notice, it's got this insert, and this insert has lines that tell you that the universe is actually accelerating its expansion. Basically, think back to Adam, Eve, and a snake. After one interval, 1 grew to 2, and 2 grew to 4. After 2 intervals, basically what you will have is that the growth will actually become larger. So 2 would not grow after 2 more intervals to 4, but actually 2 would grow to 4 point something, and 4 would grow to 8 point something. So 2 grows to, let's say, 4.2, and 4 grows to 8.4, etc. So the expansion is speeding up. This does not make a lot of sense as far as the physics is concerned, because we expect gravity to always be effective and eventually pull things back. However, that's the way the universe is. The third huge column on which the Big Bang Theory stands is the abundance of elements isotopy. Everywhere you look at those spectra of stars and galaxies, like the Harvard calculators did, but for galaxies. And you see how much helium is in each galaxy on average, not in the evolved stars, but in the youngest stars, in the oldest stars, the stars that never exploded. So that abundance of elements should be the same only if the beginning of the universe was about the same everywhere. What it means is that in the first 3 minutes or so of the universe, as we go backwards, the temperature was just right for making helium from hydrogen, the same way as they're being made in the middle of the sun. So we had a little bit of creation of helium from hydrogen in the beginning of the universe. Now, if that's the case in a galaxy in one direction and in a galaxy in another direction, that's evidence that both of them were the same. Now we're talking, of course, about not very active galaxies, but galaxies where we have mostly stars that have not even burned the original core of hydrogen into helium, so that we can look at their outside and see matter as it was 13.7 billion years ago. And since in that case all of the elements seem to be the same in all directions and actually not that different at very different distances, that's a huge support for the Big Bang Theory, the fact that the universe was hot and dense at a certain point. Now here comes a huge fourth column that supports the Big Bang Theory and a question that's related. In 1965, the forefathers of satellite phones, Penzias and Wilson, were working to see if they can actually broadcast microwave into space. What they were concerned with is that there may be some stars or active stars, etc., that would make disturbances. So they tried to find out what the frequency was of those stars. To their amazement, they found out that microwave hiss is coming. Okay, it's microwave, it's light, of course. We're not talking about any sound. So it's light with very long waves near the radio, called microwave, and in all directions they're aimed their weird antenna at. it's called the shoehorn antenna they found radiation, and that radiation was in the form of a black body with its peak. If you remember, the peak of black body radiation tells us, for example, if it's blue, it's incredibly hot. If it's red, it's less hot. If it's infrared, it's less hot. Well, this was as if there was a black body out there radiating at about 2.7 above absolute zero. Here is the spectrum of a black body from whatever it is that Penzias and Wilson discovered. Now, the wavelength is in centimeters or hundreds of meters. Compare that with wavelengths of hundreds of nanometers for red, orange, yellow, green, blue, indigo, violet. That means it's a way, way longer wavelength. What it is a wavelength that has been greatly stretched. As you go further and further and further from Earth, you're going to galaxies that move faster and faster away, until you reach the time when galaxies actually formed, and even beforehand, when the whole universe was brilliant with light, shining at around 4,000 degrees. At that time, what happened was that the radiation was freed to go. So we're seeing the time the radiation is freed to go. There were basically the whole universe was almost as hot as the surface of the sun, and then it started clumping to form galaxies. To first order, to first degree, this is incredibly uniform. In every direction Penzias and Wilson looked, they found the same amount of radiation coming from that echo of the time when the universe was hot and dense. So incredibly uniform and smooth that you can't see variations that are larger than 1 part in about 100,000. Still, if we are to find evidence that from that echo galaxies formed, we want to find those 1 part in 100,000 kind of variations in the microwave. The instruments we are seeing, the instrument in the previous slide was from the COBE satellite, then there came WMAP satellite, then Planck satellite. All of them were done so that you could measure those tiny fluctuations in that echo from the early universe. Precision is so important that 2 of those 3 satellites were not placed in Earth's lower orbit, but at what's called the Lagrangian point, which is basically at the shadow of Earth, far from sunlight, in a way that it's very dark and very cold, and we can see very, very precise variations. In this and the next few pictures, we see this again panorama of the whole universe, the whole night sky and day sky, basically the whole sky, but we're seeing the fluctuations. It's not easy to determine those fluctuations. For one thing, we are moving relative to that background. So that red and blue at the very top is the very first thing that we have to subtract in order to find those variations in the microwave background. Then if you look in the second picture, we have to erase that dominant feature in the middle, which is our own Milky Way galaxy. Then we're left with the variations. This picture is from the first COBE satellite that came up in 1991. This picture that was already doctored for our own motion, and the Milky Way was subtracted. That's the picture that shows those tiny variations, one part in 100,000 or less. And it's from WMAP, Wilkinson Observatory, that was looking at those variations. First results came in 2003. So we had COBE in 91, WMAP in 2003. Planck results were only up last year. So those tiny variations that you're seeing here in more detail came from the Planck satellite. Why are these so important? Let's put those variations and look at what are the variations like. And that would come in the next slide. When we look at the fluctuations as function of size, which means let's look at large fluctuations, smaller fluctuations, tinier fluctuations, etc. See if they basically are disappearing. What these fluctuations are telling us, and this is kind of like maybe striking a gong for the whole universe, or striking a drum, some sort of a standing wave of the whole universe, that's responsible for those variations which will create on the very small scales galaxies and clusters of galaxies. Here in the results from the Planck Observatory, angular size of 0.07 degrees corresponds to about 10 to 20 million light years, which means that includes us, Andromeda, a few other galaxies, so somewhere in between our local group of galaxies and a slightly larger cluster. So even at that level we can see that there are fluctuations, therefore they could give rise to galaxies. How exactly they're giving rise to those galaxies can be told from this graph. In a sense, we call it something like the bottom down, meaning huge galaxies form first, then they collide with each other and create most of the galaxies that we see today, the disk and elliptical galaxies.